When using a language model to make small updates to document your code, there's a way to significantly speed up responses. OpenAI have called this predicted outputs, Cursor call it fast apply, and really they're both special cases of a technique called speculative decoding. The idea is that if you can make a reasonable guess of what the output should be, you can do a forward pass on that guess and keep all of the correct tokens and only recalculate the ones afterwards that are wrong. So in this video, I'll explain how predicted outputs, fast apply or speculative decoding works, and then I'll walk you through an example of how to do this using OpenAI's API or using open source models with vLLM. So here I am in Cursor, which is VS Code, but with it's a clone or a fork of VS Code that provides a coding assistant. And I've got this script here that I've written called Buggy Code. I had an LLM write it for me. And I just want to show you how fast apply works with Cursor, which is one way of doing speculative decoding. So on the right-hand side here, I've got a pane where I can chat. And what I can do is ask for a function to be updated. So I can say something, for example, update the name of the add student function to add, I don't know, big student. Just make a change like that. And now Cursor, which has access to this document, is going to provide a response. And here it's just providing, I think, a normal generation. There may be some speculative decoding used, but where fast apply is used is when I now want to make this edit. So you can see really all I want to do is change the name here. I don't want to change anything else. So all of the rest of the code should really be the same. And so what I want to do is speed up the generation speed for replacing all of this. Now, if I click apply, you can see that this is applied almost instantaneously. And there's a few ways that you can achieve this speed up. One way to do it is you can run the generation of this full new script so I can replace it quickly in advance of me pressing the apply button. Another way is that you can use regular expressions in order to match and pull out exactly what needs to be changed, although that may not be fully robust. And a last approach is you can use fast apply, which is where you use speculative decoding, basically to predict that pretty much all of the outputs, so all of the piece up as far as here, is going to be the exact same. Then there's a small change, and then you can make a prediction that the continuation is just going to be the rest of this file here. And so all of those tokens can be decoded at once. Now, if this doesn't make sense, don't worry, because I'm going to explain it in more detail here with a simpler example. And after I've done that, I'll show you how to use OpenAI to use their output predictions. And then I'll show you also how it can be done with open source models like vLLM. And finally, I'll make a few comments on costs and pricing. If you want to use this, does it save you cost? No. Does it improve the speed of the response? Yes. So here's typically how we do decoding in a language model. We have a sentence like the quick brown, and we are going to predict the next token. In this case, the prediction, and it's confusing because I normally use prediction for the next token in a language model. So I'm going to say generation instead. So we're going to seek to generate the next token here, and we have the generated token fox. Then we'll tack that on and we'll generate the next token. So we're recursively generating the next token given a sequence of prior tokens. And that's how typical decoding works. So in terms of the inference time, we typically have to wait for the information from these three tokens to be processed. Then we generate the first token. That's called time to first token. And then we're actually able to use some of the calculations to calculate fox. We're able to reuse those combined with more calculations to calculate jumped. And the reuse is called reusing the KV cache. And that provides some speed up. So generally there's some delay until the first token, and then there's a smaller delay for each next token we generate. Now in speculative decoding, we kind of short circuit that process because instead of just decoding or generating the next token, we try and generate some future tokens. Now the reason we can't generate future tokens in normal decoding is because there's no way to guess, or there's no way to calculate the token jumped until we've access to what this token is. If this was dog or if it was bear, then this may not be jumped. So there's no way to calculate ahead. This is the limitation of something that's recursive in nature or autoregressive. But in speculative decoding, we do make some parallel decoding or generation by using our guess. And what this involves is, just guessing what the next tokens are going to be. So here I'm guessing Fox jumped over. And because I have guesses, that frees me up to make these calculations here of what the next tokens will be, not just for brown, but for Fox jumped and over. Now, of course, if these guesses are bad, I'm going to be wasting flops or floating point operations on calculating the next token after over. And if over turns out to be wrong, then I'll have just wasted that compute. So this only works if you are able to make good guesses of what the future tokens are. And if your guesses are good and these turn out to match what the predictions of the next tokens are, then you're done. So here, if I just want to generate as far as I've correctly guessed the next tokens, and so I can accept Fox jumped over, and I can accept that. Now, if I'm wrong, so for example, if my guess is Fox jumped 4, here you'll see the next token after jump is generated as over. It does not match my guess of 4, which means that this calculation of A is not going to be useful and will have to be thrown away. However, I can keep Fox jumped and over, and I can now just recalculate, do another forward pass to calculate the next token after over, which is going to be there. And so the benefit of this guess is I'm able to basically at the same time get 3 tokens in this case, if I make 2 correct guesses, or 4 tokens in this case in a single forward pass, instead of just getting 1 token Fox and having to regressively calculate the rest of the tokens. So the question is now, how do you make these guesses? And there are a few different ways. One is to use a smaller, faster model. For example, for Llama 8B, you might run Llama 1B or 3B in order to generate some future tokens. Now, why does it have to be smaller? It has to be smaller because it has to be faster. The guesses need to be there in advance of the bigger model making its generating new tokens. The second option is you could just use some sequences from a prediction the user provides. And this is the OpenAI approach, whereby there's a field when I make a call to the LLM that is for the prediction. And I will just provide a chunk of text, and this chunk of text is used, sequences are used from within it to make reasonable guesses of what the future tokens might be. And the last approach is you could just use some sequences from the prompt. So often when we want to correct some code, then the code or much of the code we're going to generate is actually already in the prompt. And so just by using the prompt, we can make some predictions. And that's how the vLLM approach works. This is called n-gram speculation, n-gram because it takes n series of words and it uses those to make a prediction. And I'll explain how that works in a second. So before I show you how OpenAI's API works and also how to run vLLM, let me just show a very simple example of how you use the prompt to generate good guesses. So here's a question: fix this code. 11 plus 11 equals 23. So of course it should be 22. And the process that will be gone through by the LLM or the inference engine is first generate a few tokens. So say generate 11 space plus. And then if we have this initial sequence, we can use that to search within the original prompt. So we search within the original prompt and we find 11 plus. And what we can do is just as a reasonable guess, we can use everything after that plus. So our reasonable guess is going to be 11 equals 23. So now we will forward pass on that guess. And what we're going to find is that the correct tokens or the generated tokens will be 11 equals 2. But the 3 will not be correct because the generated token there, if the language model is indeed correcting our code, should be 2. So we'll forward pass on the guess here. And we're going to find that we can keep the 11, the equals, and the 2. And then we'll have to run a new forward pass to calculate the wrong token. So we'll have to do a new forward pass on this 2 here to calculate the correct next token, which should also be a 2 because the answer is 22. So if we go through the steps, generate a few tokens, 11 plus, use that to find a reasonable guess in the prompt, keep the correct tokens, which would be 11 equals 2, and then forward pass again to get the final token here. So this is the example of vLLM. And you can see that this is pretty much how OpenAI will work as well, except you're searching for these n-grams or good guesses, not in the prompt, but in the prediction text that you provide to the API. So with that, I'm going to move to demo of the OpenAI API and how you can use predictions to speed up inference. And then I'll show you how to do the same with vLLM. And then I'll make a few comments on costs pricing and business model that companies are using for these predictions. So for this demo for OpenAI and vLLM, I'll be working out of the Advanced Inference repository. You can purchase lifetime access at trelis.com/advanced-inference. So I've cloned that repository. It contains scripts for a wide variety of different inference techniques, including RAG, including structured responses, citation verification, fact-checking, DSPY prompting techniques, and much more. I'll let you take a look in your own time. So I've cloned this repo, and I'm working out of Cursor, or you can use VS Code. And I've got some scripts here within the API calls and then the predictions folder. I've got a script here for OpenAI predictions, and I have a script here for running vLLM predictions. So you're going to move into that folder and set up a virtual environment, and then pip install requirements. And you'll want to add your OpenAI API key into your environment variables, which is a .env file. So put your OpenAI key right in there. And this script then is going to make some calls to the OpenAI endpoint, and it's going to ask us, we're going to ask it to fix some code. And the code is the bookie code that I provided earlier. I've asked Claude just to write me some code that contains some bugs, and we're going to ask the API to fix this code for us. And the whole idea is that because they're just small fixes, it's going to be useful to use predictions because much of the content is going to match the input code that we provide. So we do that using OpenAI and then using vLLM, and it's going to output some fixed code, and we'll measure the time it takes to respond. So before I just go through this script, let's take a quick look at the docs from OpenAI. And I'm here just on the chat completions. And you'll see that the predictions are done just by passing an extra argument called prediction. And you're just going to pass in a string of the content. So in this case, the string I pass in is going to be predicted code. And we can see that when I check through the code itself. Here's my OpenAI predictions. I'm setting up my OpenAI client. I'm going to create the chat completion. I'm going to set use predictions to true and pass in predicted content, which will be a string. And the way I'm going to do this is allow a flag for predictions, so I can run both with and without. And if the use prediction flag is true, and there is, it's down here. Yeah, if use predictions is true and there is predicted content available for us to pass in as the predicted content, then we're going to add in the request parameters. We're going to add into the request parameters this predicted content, which is just going to be my buggy code file. Then we'll make a call to the client to get a chat completion, and we'll measure the response time, start minus end, calculate the usage tokens, so the prompt tokens and the completion tokens, and how long it takes for us to generate that response. So that's my simple script there, and I can just run it by doing Python and then OpenAI predictions.py. And if I want to run that with predictions, then I'm simply going to append the flag, which will be for predictions, and we'll see how that performs. Now, notice that this this buggy code is quite short, so there's only a small potential for time savings. If you have much longer code and you just have a small error within longer code, that gives you a much greater chance to save time. So here you can see it took us about 12 seconds without using the predictions. And if I now do it with predictions, so predictions, I think we will see some small kind of improvement in the time. So when we run it there, you can see our completion tokens have actually increased. We've got 616 instead of 500. By the way, I've capped it at 500 actual completion tokens. The reason we've paid for more completion tokens is because there were some wrong guesses, and that meant there had to be extra calculations to fix those guesses. So you'll find that your completion tokens will always be at least the number that you have without predictions, but usually it will be larger. Also, you can see there are some extra prompt tokens in this case too. Now, we didn't actually get the time saving here. So in this case, I think just due to randomness, we didn't get some improvement. We can take a look though. I did a few more runs, and I'll show you now the graph of those runs. So here we have the graph of OpenAI. So when I repeated this a few times, I found that with speculative decoding, I was able to get 82 tokens per second. This is not time for response, it's average tokens per second, whereas with standard decoding at 66. And as I mentioned, with longer files, you've more potential to save. With shorter files, and if you have a lot of changes, then potentially in some cases it might even be slower, or it really depends on how the GPU architecture is set up. So I'm going to show you the vLLM approach now for how this works. And you can see here just in advance, in this exact same problem, I was able to get a speed up from 51 tokens per second to 77 tokens per second by using speculative decoding. Now it does require tuning of some hyperparameters, which I'm going to show you now as well. So let's go back into VS Code and find the README. Within the README, you'll be able to find a one-click endpoint for setting up vLLM. So I'm going to run it on RunPod. And actually, I've got a specific endpoint that allows you to use predictions. So we'll take a look inside. First, we have to pick a GPU. So I'm going to use an A40, which is one of the cheaper GPUs. And then within the pod, I can take a look just to see the configuration. And if I increase my screen size here, you can see that we're running with vLLM, the latest Docker image. We're using the Neural Magic FP8 model, and we're going to run with a max sequence length of 8,000. And here's what's important for speculative decoding. We're going to specify the model as being n-gram, which means it's going to fish for sequences within the prompt. Now, you can also use a model like Llama 1B or something as a speculative decoding model. That's also supported. But here, the whole point is that we want to use sequences from the prompt. Next, we're going to specify the number of speculative tokens. So this is how many tokens in advance you want to speculate on. And yeah, there's going to be an optimal number, because if you have a really long document, you actually want to speculate really far in advance so that you can just in one shot complete as much as you can. Of course, there are limits as to how many will actually fit on a GPU for the one calculation. So that's a more detailed factor. And there's another matter here, which is how many different parallel sequences do you want to look up? So you can not just make one series of guesses, you can make a few guesses in parallel and just keep the ones that are correct. And of course, that'll cost you more tokens, but it increases the chance of getting it right, so it can increase your speed. And basically, it makes sense to increase this if you've got space on your GPU. So if you're not doing a lot of heavily parallel inference already, it can make sense to just use up that GPU bandwidth by doing more speculation. So yeah, in the background, and say for OpenAI, there are a lot of considerations around what the best parameters are around the size or the length of the speculative decoding that you want to do. So the length of n-grams you want to pull, either from the predicted input that's given to OpenAI, or in the case here of speculative decoding, the length we're searching for within the prompt. So I've got this up and running. It's going to take a few moments to extract. You can see the CUDA graphs are building. And once you see all these routes displayed, you should be ready to hit that endpoint. So I'm setting the model name, the API endpoint from environment variables. And I'm going to use an OpenAI style endpoint, even when I'm calling vLLM. So I'm initializing the client, and I'm going to now parse my input. I do allow for a truncation of the code or the prompt that's being provided. So I'm just going to truncate if it goes beyond, I think, 20,000 characters. That I think will fit all of the buggy code example. Then I'm going to define a function to do a chat completion request. This is very much the same as OpenAI. Measure the time for response, measure the completion tokens, the prompt tokens. And by the way, the completion tokens here, I think, will just provide you with the actual completion. It won't tell you how many were used for speculative decoding. I'm not entirely sure on that, but as far as I remember, that's what it does, which is a bit different than OpenAI. And then we will just print out the buggy code to a new file that will be called buggy code fixed. So here I can just run Python and then vLLM predictions.py. And I'm going to run with the defaults on context length. And here in my .env file, I've just updated pod ID within the API endpoint, and I've got the model here. So I should be ready now to hit that endpoint. And you can see here, I'm getting about 17 seconds. Often one of your first requests will be a little bit slower with vLLM. There's some kind of warm-up dynamics. But in any case, this is how you can run it. And then you go back, adjust the speculative parameters, maybe to something a little bit smaller. And then you can remove them completely if you want to compare how things perform without using any speculative decoding at all. Now, I did do a few runs with different values for speculative decoding, and that does affect the performance. I can show you that right now within my README. So I ran 3 different examples. In the first example, which is without any speculative decoding, I was able to get just under 10 seconds. And then I used speculative decoding with 100 speculative tokens and 4 prompt lookups in parallel. And this actually slowed things down to about 14 seconds. But then when I did it again with a smaller number of speculative tokens and a smaller number of parallel prompts, I was able to get the time down to about 6.5 seconds. So you will need to play with the numbers here. My recommendation is actually to use smaller numbers because that's going to be more flexible. If you use very long advanced speculations, it's only going to work well if you actually have a lot of very long predictions that are going to be correct. And those predictions have to be in the prompt in the case of vLLM. So probably it is better to use smaller values here to guarantee you do get some speed up using speculation. Now, just a few notes around costs and pricing before I wrap up. So if you're using predictive outputs or speculative decoding and you are correct on your prediction, then you're going to have roughly the same number of calculations or floating point operations, in other words, cost, and you're going to have less frequent movement of weights if you're able to set up the GPU in a way that when you move weights to the GPU, you do multiple parallel calculations at once. And the full response will be generated much more quickly because you're doing one forward pass, ideally, and computing all of the next tokens at once rather than doing them in an iterative way. So this is your best case scenario where you approximately asymptote towards the inference time for just one token, but with many tokens. Of course, in reality, your predictions are not always exactly correct. I mean, if they were, then you wouldn't do the inference in the first place. So because some of your predictions are only partially correct, that means the wrong predictions have to be recalculated. It means that your speed up is not going to be quite as fast. Your partial response will be generated asymptotically in the time of one token, but then you'll need to go back and make more calls as per usual with a regressive process. And with respect to GPU utilization, maybe your GPU utilization is somewhat better because you're loading the weights and doing more parallel processing at once, but it really depends on the nitty-gritty of how your inference stack is set up. And that's not something you're easily going to control because that's what OpenAI is controlling, or even with vLLM, that's something in the internals of vLLM. Now, in terms of product packaging, OpenAI have made a design decision that you can provide your predictions instead of just relying on them generating n-grams or sequences from your prompt. So why would they do this? Well, I don't have any inside information, but my guess is when you specify a prediction, it narrows down the field of guesses to just the token sequences within that prediction, as opposed to potentially guessing from any sequences within your input. Now, at the same time, generally, if you are matching some early token predictions, because you already have a few tokens, generally you can fairly actually find good guesses within the prompt. So I'm not entirely sure there's a massive benefit to requiring the user to make a prediction, the benefit being slightly better guesses and less wasted tokens. Of course, it adds a bit more to the UX for developers because now you have to explicitly provide a prediction. So that's the drawback with the OpenAI approach. You explicitly have to provide what your prediction is going to be. Whereas with vLLM, you can just turn on speculative decoding and it's going to find n-grams within your input. And that's my overview of output predictions or speculative decoding. If you want to try out vLLM, you can access that one-click template in the public repo. That's one-click LLMs. You can find that repo on the Trelis research organization on GitHub. You can find the entire scripts for this video over at trelis.com/advanced-inference. And I'll put links to all of that below. In the meantime, let me know if you have any questions in the comments. Cheers.